Hi everyone, my name's Aashka. I'm a psychology neuroscience major here at UF. I'm on the pre-med track, so I studied for the MCAT, and I found that there were a lot of questions on light and optics, which is what I'll be talking about today. So the first thing we're going to talk about are mirrors. And there are two different types of mirrors. The first one we're going to look at are concave mirrors. So for concave mirrors, you can have a real image, and if you have a real image, it will be inverted, and the position will be greater than the focal length. And I'll explain what that means right over here. So we have a concave mirror, and we have our person. So for a person, our focal length is going to be right here, this orange dot. And we're going to draw our image. So to draw our image from our person, we're going to draw a parallel line to the mirror, and once you draw that parallel line, it reflects through the focal length. Kind of like that. And then the next one is going to go through the focal length, and it's going to reflect parallel. And then you find the point of intersection. So for us, it's right over here. And then we draw our image, which is going to be inverted, like we said. And that's the image we get if it's real and it's a concave mirror. So for next concave mirror, we're going to talk about the virtual image. So if we have a virtual image, it will be upright, and the position will be smaller than the focal length. So what's that going to look like if we have our concave mirror? And I'm just going to extend it to the other side. We have our focal length, which is our orange dot, and our person. So similar tips for the rays. The parallel lines go through the focal point, so it's going to reflect through. Our guy's head. So it's going to go through. And because it's a virtual image, we're going to extend it to the other side. And then we're going to go through the focal point to the mirror. And this is our reflection, and we're going to extend it to the other side. And on the other side, we have our virtual image that is upright. And as you can see, it's also a lot bigger. So next we have convex mirrors. And convex mirrors have virtual images that are upright, but what's different is that the image is smaller. So what's that going to look like? We have our convex mirror. And in convex mirrors, the focal point is on the opposite side. So here we have our focal point. and our person. So when we draw our parallel line, it's going to reflect, but it goes through the focal point. So it's going through the focal point on the other side, and it reflects this way. And then we go through the focal point, and that reflects parallel. So I just drew that to get an idea of what the line will look like, but it's going to reflect parallel. So that means we look at our point of intersection, which is right here, and our image is on the other side, which is why it's virtual. It's upright, and it is smaller. Okay. So a few equations to keep in mind. We have 1 over f, which stands for the focal length. 1 over dO, which is the distance of the object, plus 1 over di, which is the distance of the image. We also have magnification equals the height of the image over the height of the object, which is also equal to the negative distance of the image over the distance of an object. And the last thing we have is the focal length equals 1/2 r, which is the radii of the curvature. So now we're going to use some of these equations for one of our problems. So our problem is we have a convex mirror, and it has a focal length of -80 centimeters. And we have a cyclist that is 1.5 meters tall. And the cyclist is 28 meters from the mirror. So you are also there, and you are 1.4 meters from the mirror. And something to just keep in mind is that you, the cyclist, and the mirror are all in one line. Okay, so these are some things that we need to know. So if we look at it, looking at all of this, what can we pick from it? So we know that our focal length is -80 centimeters, but our other units that we have are meters, so we want to make sure that's all the same. So we have 0.80 meters, and our height is 1.5 meters. So 1.5 meters. And we have two distances, so I'm going to define it as the distance of the cyclist is 28 meters, and the distance from the person, or you, to the mirror is 1.4 meters. And our question is, how far are you from the image of the cyclist? So to solve the problem, one thing I did forget is the negative sign for the focal length. So just to remember, concave mirrors have positive focal lengths and convex mirrors have negative focal lengths. So to solve, what we're going to use is the equation that we wrote down earlier. 1 over the focal length equals 1 over distance of object plus 1 over distance of image. So the two knowns that we have here are the focal length and the distance of the object. Right now we're looking the distance of the image. So our focal length, we have 1 over negative 0.8 equals our distance of the object is the distance of the cyclist. So that is 28. And we're looking for the image of the cyclist. So you would just subtract . And then after solving for that and finding the inverse, we get that the distance of the image is a negative 0.78 approximately. But we don't stop there because our question is, how far are you from the image of the cyclist? We know the image of the cyclist, but we don't know how far we are. So if we were to look at an image of what exactly they're asking, our convex mirror would be like this. And basically our cyclists would be behind a distance of 0.78. So this is 0.78. And we want to see how far are we. So we would be somewhere over here. And we know that we are a distance of 1.4 from the mirror. So this is 1.4. So if we want to see how far we are from the image of the cyclist, we would look at the absolute value. So we would add our distance, 1.4, and add the distance of the image, which is 0.78. And we get a distance of 2.18 meters. And that would be our final answer. So next we're going to talk about lenses. We have two different types. So first we're going to focus on converging lenses. Converging lenses they also have two types of images. So first we're going to look at real images. We have a real image. It's going to be inverted. And what does that look like? We're going to draw our converging lens right here. And our lenses have two focal points. So here is our object. And we have, actually, I'm going to make our object just a little smaller. So we're going to have our parallel line go through, and it's going to go through our focal length on the other side, and then we have one go through the center from our object. To the other side. So then we see our point of convergence, which is right over here. Mixing this. So then our image is real, but it is inverted. And it looks like this. So our next type of converging lens is if we have a virtual image. So if we have a virtual image, it's going to be upright. We're just going to draw our lens again. And our two focal lengths. So if we draw our object on the inside, our lines, so our first line is going to go parallel and through the focal point, but we're going to extend it backwards. And then our other line is also going to go through the center, but we're going to extend it backwards until we find our point of convergence. And that gives us a virtual image that is upright. So the next type of lens that we have is a diverging lens. And diverging lenses give us virtual images that are upright. So to draw our diverging lens, we have our lens here. And similar thing, we have two focal points. And here is our object. So our first line is going to go parallel, and we're going to trace it back to our focal point, and it comes out of the lens diverging. And then our next line is going to go through our other focal point on the other side. And it comes out of the lens parallel. And then we're going to trace it back until we find our point of intersection, which is right here. So our image is going to be virtual but upright. So now we're going to try a problem. And we have two lenses, actually. So first we have a converging lens, and then we have a diverging lens. So this is lens 1 and a lens 2. So for lens 1, the focal length is 5 centimeters, and for lens 2, it is going to be -8 centimeters because it's diverging. And our object is right here. So our distances, this one is 4 centimeters. And this distance is 12 centimeters. So, and one thing to know is that our object, the height, is 1 centimeter. Okay, so that is a lot of information that we have. So the question that we are answering is, what is the distance of the final image? So I think the easiest way to answer this question is to break it into parts. So part 1. So for part 1, we'll focus on lens 1. And we're going to use that same equation that we looked at earlier, which was, I'm going to write it over here, 1 over focal length equals 1 over distance of object plus. So we're going to look at that equation. So in this case, for the lens 1, our focal length is 5 centimeters. Distance of the object is 4, and we're looking for the distance of the image. And our units are centimeters. So if we subtract, and then we solve, our distance of the image is going to be negative 20 centimeters. So it's negative because it's going to be in front of lens 1. And we're going to take that and look at lens 2. So looking at lens 2, our same equation. So we have, but we're going to use the focal length of lens 2. So we have 1 over negative 8 centimeters. And our distance of the object is not going to be 20 centimeters because 20 centimeters is in front of lens 1. So we want to take into account the distance between the two lenses. So that means our distance is 20 centimeters plus 12 centimeters. And we're looking for the distance of the image. So we're going to subtract. And I'm just going to add that to simplify it. So 32 centimeters. And once we solve it, we get that the distance of the image is negative 6.4 centimeters, which means it's 6.4 centimeters in front of lens 2. But the final image of the distance, we want the distance of the final image of the object. So we're going to look at it from its original point, which was right here. So if it's 6.4 centimeters in front of lens 2, we want to look at the difference. So that means the final image is going to be we're gonna do 4 centimeters, which is the distance between the object and the lens, plus 12 centimeters, but we're gonna subtract 6.4 centimeters. And that will, the 12 centimeters minus the 6.4 will account for the difference between the two lenses to find the exact location of our object. So our final answer is 9.6 centimeters. And that means it is 9.6 centimeters from our initial point, which was right here. So looking over our work mathematically, it all looks right. I just wanted to actually correct myself for our drawing here. I drew our object in line with our lens, but it would actually be in line with the center. So I'm just going to redraw it really quickly right here. And we would have it go through the center right here. And here is our converging lens and our object. And just to clarify where the focal points would be, our object is at a distance of 4 centimeters, like we said earlier. And our focal point is 5 centimeters, so it'd be just outside over here. And around over here, 5 centimeters. And this distance we have is 12 centimeters. So our focal point on the other side is going to be past our yellow focal point going left. So it would be over here. And on the other side, if we were to extend it, somewhere 8 over here. So both 8 centimeters for the blue, and for the yellow, 5 centimeters. So that completes today's lesson. We talked about mirrors and lenses. Thank you for joining. I really hope this helps you whether in physics or just on the MCAT as well.